Hey everybody, welcome back. So today is very exciting because we're going to be making a pseudocode for the gradient descent algorithm for simple linear regression, and it's basically the exact same thing for every single other function and machine learning algorithm. They pretty much all do the exact same thing, which is just with respect to whatever parameters are involved and trying to learn in the function, we're trying to learn beta naught and beta 1. And if we're trying to learn whatever else we decided to call it in our function for machine learning, all we're going to be doing is gradient descent, where we look at our cost function, it's the MSE, it's this thing, and we take the derivative with respect of this function to all the parameters. We get it with that, and if it was a different machine learning algorithm, whatever those parameters are. And then we keep doing the same thing, where we just, whatever our current values of beta naught, beta 1, and our other parameters are, we're going to keep just going in the direction, or the opposite direction of the derivative. We're going to keep going down, and down and down and down until we hit the bottom. Okay, so we're going to derive this and write the actual pseudocode today. And if you look elsewhere, you might see something different. There's many variations. And to be honest, the actual TensorFlow or PyTorch or R, whatever is using this stuff, it's not going to be using just base gradient descent. We will look at a couple different ways to look at it eventually. But for now, just think about this algorithm and know that it's basically what pretty much everything is doing. Not quite, but pretty much what every program is doing, so that we can get the right parameter values to get a local minimum. Okay, remember, local would mean if we had something like this, okay, we would start here. If we started here, we'd actually end up here instead of getting this global minimum. Okay, so we get a local minimum with respect to all of our parameters. Okay, so to do this, well, we have our derivatives right here. And so basically, we can just formalize the argument here. So basically what we said is that you can keep moving in the negative direction of the derivative. So my update rule, the update rule, which is how we go from one value of beta naught to another value of beta naught, or how we go from one value of beta 1 to another value of beta 1. That is, a progressive jump like this. So we can define this jump by writing beta naught. I'll write t plus 1. Okay, what we mean by this is the next value of beta naught. Okay, so for whatever it was before, it was beta naught t, like this. Okay, so this is beta naught t. This is the previous value. This is the updated new value. So the new updated value is going to be the old value minus the derivative, m partial MSE by partial beta naught. Remember, this is going to be a value, okay? So this is going to be evaluated at our current value of beta naught and all of our data, okay? So we're going to plug in this value, and we have a current value of beta naught and beta 1. And so what I really mean here is this is going to be with respect to beta naught t, okay? So there's different ways of writing this. What I really mean is the derivative of the MSE with respect to beta naught evaluated at that beta naught is equal to the old value of beta naught. Okay, so this beta naught here, that is involved in the function, that value is going to be the old thing here. Okay, so it's our old parameters. And so all we're doing is getting our new value. So new value is going to be old value minus the derivative with respect to that value, the derivative with respect to that parameter value. And then we're actually going to multiply this by something called alpha. Okay, so it's going to be minus alpha times this thing. And so I'll just write it over here. And so what this alpha thing is, that's basically also specifying how big the jump we want to be. Remember, this should make sense because we want to subtract it. Why do we want to subtract it? Well, again, think about it. If we had some current value of beta naught t here, and then we'd want to get to a new value of beta naught t plus 1, which was probably something over here. Well, the derivative here, well, this is positive. Okay, so this is a positive derivative, and it's relatively steep. So the amount we want to move is, some amount relative to the derivative. Maybe it's a lot. And the direction, well, if we're subtracting it here, we're always going to subtract it. So if this value is positive, we're subtracting a positive value, which means we're actually decreasing the value of beta naught. So we'd move to the left. Okay. And it's the same thing if we were instead over here with beta 1. Okay. Well, the value of the derivative is going to be negative. Okay, so it's something like this. It's a negative derivative. Well, if we're subtracting a negative derivative, well, that means that we're subtracting we're basically adding. Okay, so we're adding a positive number. And so we're going to the right, which is good. We always want to be going down to the direction where we minimize the MSE. And so this is right. Okay, so that's what I mean. If you didn't totally understand what I meant by the opposite direction of the derivative or the negative derivative when I was saying that, I mean here, we're going to subtract the value off of it. That's how we force it to go in the direction that we want to go. And it's actually going to be based off of the value of the derivative itself. That's the magnitude of the push. The value of this thing dictates how far we go, as well as this alpha thing. Okay, so we also have alpha, and that is just some number. Okay, so this is just what we call a step size. Okay, it's a parameter, and it has to be bigger than 0, because if we allowed less than 0, that would kind of mess up the direction we're going, and that we don't want that. So it's just a scale factor that says if this is a million, it means we're going to take huge jumps. Like if alpha was something massive, we're going to jump like from here to all the way to there, which is crazy. We don't want to do that, because then if we did the jump again, we decided we had to go this way, well, maybe we'd end way over there. And so that's called, I'm forgetting the term right now, like overstepping, basically, overstepping. Okay. So we don't want to overstep, we want to hit it well. And so to do that, we pick a relatively low value of alpha. Okay, it's just some number, you pick it. And so that way we'll go smaller and smaller results. And the trade-off is that the smaller the alpha you choose, the smaller you jump, and the slower it's going to take. Remember, if you've heard about machine learning algorithms taking a long time to learn, especially these huge deep learning models, well, this is something involved. You pick something like the alpha, and if you pick something too small, well, then you're going to be going really slowly, and that could be an issue. But if you go too big, then you're going to be jumping over the minima, and you're going to be jumping past it, and that's not going to be good at all. Okay, and that's pretty much the algorithm, but what I want to do over here is just formalize this into a loop that we can really easily turn into actual Python code, and we can see how this works. So basically, we want to do this in a loop. All right, so we're going to have something that's maybe while true, and I'll find a reason to exit the loop eventually. We're not going to talk about that just yet. And so what we want to keep doing in this loop is update beta naught and beta 1, but to do that, well, we need to do a couple things. We need to do initialize, so I'll just write init beta naught, beta 1 in the reals. Okay, so all I'm saying by this is just choose some number for beta naught and beta 1, -5 and 1. I randomize them, I don't care. Pick some values for it. And so after we've picked these values, well, now we can update them because we have legitimate values. We've received our data, by the way. We're going to assume that we have some training set of data, which is x and y pairs. Okay, so we have beta naught and beta 1, we have x and y pairs, and we have also to define alpha. So choose alpha greater than 0. All right, because then we need you just choose some value. It could be 0.1, 0.001, 5. That's a huge value, but you'd pick some value that's bigger than 0. Just choose one. And then we're ready to start looping over this thing. So we just apply the update rule, and really all that we do is exactly the same thing here. So I'm just going to plug this in, is you just do this. You do beta naught is this updated thing where we take whatever it was and then we subtract away some value times the derivative. That'll get us in a little bit in the right direction. And then we're going to do the exact same thing over here. We're going to do that with beta 1. Okay, so we update that, good to go. And now we just need to know when to end the loop, because this is going to keep running. We're going to keep doing this forever, except a really easy way to end the loop is just to do something like iters. Okay, iters is just a way of saying number of iterations. Okay, so I choose some value of iters greater than 0, and then maybe I'd keep track of I. I'll set I equal to 0, and then every time in the loop we'll do I plus equals 1. And we'll ask the question if I is greater than iters. So if this is true, then exit the loop. Okay. And basically, we'd return beta naught, beta 1, whatever you want to do. It's just changing the parameter values somehow here. So we kept track of the values because the whole point of this was just to learn the beta naught and the beta 1 value. Okay. So that's really the gradient descent algorithm, which I'll label this above. This is the gradient descent, and I know that we haven't even talked about the gradient itself yet, because that's a vector, but really it doesn't get much more difficult than this. It's just, instead of looking at the values of particular things like beta naught and beta 1, it's just thinking about the parameters as a vector, and so that the derivative vector is a gradient, and then you change all the parameters as a vector instead. Okay, so it's really just gradient or derivative descent. It's pretty much the same thing. And yeah, I will see you in the next video when we actually take this thing and we put it into code.